So guys, what we'll do is we'll run through some exam questions or past exam questions that have come up on rates of reactions. So this is an example of one. The first question there, what is a catalyst? A substance that alters the rate of reaction without being consumed itself or not being consumed itself. So that's a relatively straightforward one. Just a big difference there between junior cert and leaving cert. Instead of saying it speeds up the reaction for junior cert, what we say in leaving cert, a more accurate one, as I said to you before, that a catalyst can both speed up and slow down the rate of reaction. So we use the word alters the rate of the reaction and is not consumed itself. And remember, it's always written above the arrow as well. Explain how the type of bond, or explain how the type of bonding in the reactants influences the rate of a chemical reaction in an aqueous solution. So aqueous is a water solution. You think of aquatics as water, and in a water solution, when we're talking about types of bonding, I mean, we're talking about there whether the compound is ionic or covalent, essentially, for leaving cert. And as we said before, in the case of covalent, something that is bonded covalently, or the molecule is covalent, well, technically molecules only refer to covalent substances, but when the compound has covalent bonding in it, then bonds must be broken for the reaction to proceed, if you like, when it's in an aqueous solution. Whereas for ionic substances, when they're in aqueous solution, they're individual ions anyway, with the carbons, if you like, or with the negatively charged end ions being surrounded by, let's say, the hydrogens of water. Of course, the reason for that is if we were to look at the water molecule, oxygen, and you have two hydrogens off it. Of course, both hydrogens, there's a lot of chemistry in water, of course, but both hydrogens are slightly positive. The reason for that slight positive charge, of course, is that they don't have a fair sharing relationship with oxygen. For junior cert, you sort of think that all covalent bonds are fair, but of course they're not. Here, the oxygen has a higher electronegativity. It will pull on the shared pair of electrons with this hydrogen, this hydrogen. The electrons will spend most of their time, or the majority of their time, around the oxygen. When I say the electrons, I mean this pair and this pair. The pair making up those two and those two. So that gives the oxygen slightly negative charge. So when an ion, like something like NaCl, is ionic substance like sodium chloride, NaCl, the Na plus would be surrounded by water molecules with their oxygens, if you like. Sort of roughly, now obviously you know water is constantly moving, it's a liquid, but roughly speaking, that sort of arrangement. And then the Cl minuses will most likely be surrounded by the positive hydrogens. In any case, you see the individual ions exist at this point when it's an ionic substance. So in essence, ionic reactions occur much faster, and the reason that is no real bonds have to be broken, and all that has to be done is a rearrangement of ions. Whereas a covalent substance, you need to break bonds, and essentially that slows down the rate of the reaction. How could you reduce the rate of the reaction that takes place in solution? There's a couple of very straightforward things. Think about the collision theory. If you reduce the temperature of the solution, that will slow down the reaction. Reducing the temperature means less collisions, and indeed less collisions with perhaps sufficient energy to give rise to the products. The activation energy there I'm referring to, of course. And then the other thing you could do as well is you could lower the concentration by diluting the solution in some way. So adding more water perhaps and making it more diluting, or to dilute it more. The other thing you could add is some sort of an inhibitor, a catalyst that slows down the rate of the reaction. And glycine actually does that for the decomposition of hydrogen peroxide. Because decomposition of hydrogen peroxide is all over your course when it comes to catalysts. So an example of that, a third, probably a pretty highbrow answer, would be to add an inhibitor to reduce the rate of the reaction. The diagram shows the oxidation of methanol using platinum wire as a catalyst. Transition metals, remember, are excellent catalysts. Anytime you see a question with a transition metal in it, assume that we're talking about it being a catalyst in that reaction. State one observation made during the experiment. Well, there's a few different things. The platinum wire itself will glow as it heats up because it's an exothermic reaction. There is the odour of methanol, so formaldehyde is quite a distinctive smell, if you like. People get it from white spirits and that as well. During the reaction, as this heats up, some hydrogen is produced, so you get a popping sound because you have the fuel, the hydrogen if you like, and you have the high temperature produced by the heating up of this wire. And methanol will boil here at the base. This is one of the things that will, as the reaction, as the temperature increases here, will boil. And essentially, sometimes you can get a high degree of temperature, you get a flame, but in any case, there's plenty of observations there. State what two major products of the oxidation. Methanol is probably the biggest one that we do have to remember. It's methanol as well, methane, and then it ending in Al as opposed to Ol. So Al is the aldehyde, and aldehyde actually comes from the premise of an alcohol being dehydrogenated, so there's a loss of hydrogen there, so that's where the aldehyde comes from, but that's more organic chemistry, but yeah, just to be clear, that's where that comes from. Water is also produced in this reaction, and then as we said, the popping sound is due to the production of some hydrogen gas. What term is usually used to describe the attachment of a liquid or gaseous molecule? So that's surface adsorption. Surface adsorption. Adsorption. And that's a little theory that's used for that as well. Be careful about the word. It's AD there, just to be clear. It's not absorption like into a sponge. It is adsorption, where it clings to the surface rather than moving in like it would in the case of a sponge. Explain how this type of interaction between the methanol and platinum affects the rate of the oxidation. Effectively, what will happen is the bonds in the methanol are weakened. That's essentially what happens, and because they're weakened, this lowers the activation energy, and therefore the reaction can occur more quickly. That's probably the easiest and the shortest way of saying that. Explain how a catalyst poison like sulfur, effectively it inhibits or blocks the catalyst by blocking its active site. So it essentially just blocks. Something like sulfur will block off the metal catalyst that is platinum. And that's the easiest way of thinking of it. Sometimes people study biology as well. They talk about the damaging of biological catalysts by changing shape and that. But blocking is another one. Explain the term activation energy of a reaction. The activation energy is the minimum amount of energy, effectively, that colliding molecules must have for the reaction to take place between them. So activation is the energy, the minimum amount of energy that colliding molecules must have. And you know that for molecules to react, they must come in contact with each other. They must collide. And when they collide, then you get the product. But it's like eggs rolling around in a bowl. It's not enough that the eggs roll around. They must knock off each other with sufficient energy such that the eggs break. And then you have the breaking of the egg, if you like, is the activation energy. Here, it's the breaking of the bonds normally. In the case of covalent molecules, it is at least. Sketch a reaction profile diagram for the exothermic reaction. An exothermic reaction is one exo. So animals that have an exoskeleton have a skeleton on their surface. So anything like shellfish and that, they have an exoskeleton, it's on their outside. Exothermic is giving out heat. So the reaction effectively gives out heat. That means that the reactants, by their very nature of heat is lost, will have more energy than the products. Just think about that now. It gives out heat. You can't destroy energy, therefore it has to come from somewhere, and it's coming from the reactants being converted into the products there. And clearly diagram on your diagram write or indicate the heat of the reaction, delta H, and the activation energy. So that looks a simple diagram for this. I showed you this before as well. But just remember that the overall heat of the reaction is the difference in the two of those. You see the way this would be the reactants here, and this would be the products. So you see the products have less energy than the reactants. That's just a normal y-axis. As you move up, values increase. Normal x-axis as you go along time obviously increases. But this would be the heat of the reaction. That would be the difference. That would be lost to the surroundings, for the want of a better way of drawing that in there. Now you do have to, for the reaction to occur, you must get over the hump that is the activation energy. That's the sufficient energy that, let's say, reactant A and reactant B must collide off each other with sufficient energy, and that sufficient energy is this activation energy. So they must, it's not enough that they're in contact with each other, they must be in contact with each other sufficient energy such that they go over this hump, and that's known as the activation energy, denoted as capital E with a subscript that's low, written down below the level, if you like, of A, and that's the activation part. And delta H here in this case, because the reactants have more energy than the products, delta H here would actually be negative. That's something else you should know. Delta H talks about as the reactants, as you write it in a balanced equation, the reactants go to products. If there's a loss of energy, then delta H is negative. So that's something else you could add in on that one. Another exam question we could have a look at. This reaction is one of several that can occur in catalytic converter. Oh, this is cut off a little bit, but presumably it's a catalytic converter question here. Since the exhaust gases and catalytic converter of the car live for or converter of a car for a very short time, the rate of the reaction must be very high. Name two metals used in the catalyst of the catalytic converter. So any of the ones I said, platinum, palladium, or rubidium. So we said those in one of the other videos. And name two metals that two of the metals used as catalyst in catalytic converter. That's what done. What type of catalyst? To remember the type of catalyst, please don't get that mixed up with theory. So types here, the catalyst is a solid metal. The gases are the reactants, if you like. Therefore, that is, they're in different phases. Therefore, it is heterogeneous catalyst. That would be the type of catalyst there. And the next, and give one way the catalyst increase the rate of the reaction. They provide an alternative route, which is a lower activation energy. An alternative route for the reaction. Then sometimes it means weakening bonds, but essentially that's what it does. And finally, name the substance that could poison the catalyst and catalytic converter. You use lead or sulfur or silicone. Those are catalytic or poisons for catalytic converters. And in the next one, we would have an experiment to investigate the temperature on the rate of reaction between 0.05 molar sodium thiosulfate solution in excess of 3 molar hydrochloric acid solution was carried out as follows. A timer was started as 5 cm cubed. The acid was added to 100 cm cubed of the sodium thiosulfate solution in a conical flask, and the value was obtained and the time was taken over a certain observable stage. The reciprocal of the time 1 over time was taken as an approximate measure of the initial rate of the reaction, and this procedure was repeated at different number of temperatures. The temperature of the corresponding values. Explain the term rate of reaction. So the rate of reaction, as we define it as the change in concentration per unit time of any one of the reactants or products. Reactants, I think normally people write right, but yeah, one or the other. And describe and explain the change observed in the conical flask during this reaction. This is HCl added to thiosulfate. So essentially what will happen is you will have the production of sulfur. So it will become cloudy as sulfur is produced during this reaction. That's essentially what will happen. And then describe how the observed was used and explain. So you need to say that it was sulfur first of all, or second of all, sorry, cloudy. The solution becomes cloudy, and it's because of the presence of sulfur. Describe how this observed change was used to obtain the reaction time. Effectively, you took the time. In this case, you put a conical flask, and you place the conical flask on top of a page with an X written on it, and then you look downwards into the conical flask and you time the length of time it takes for this X to obscure. And essentially that means that the more sulfur that's present in the conical flask here, the X will become less and less clear, and when it's obscure you stop the clock. Plot the graph of the 1 over time. So we could have a look at that. That's essentially what this looks like, 1 over time, and there you have the reaction. You have temperature 10. This was taken at, let's say, what would that be, 11 or 12 degrees there, and there's the other temperature, or that's 12 degrees, and then you would have that up at 23. Another temperature was taken at 39, and then another one was taken at 47, and finally another one was done at 57 degrees. So each of those times were taken, and then the time for the X to obscure was plotted and divided into 1, giving you 1 over time, and that's the kind of curve you end up with. Use your graph to find the value of the time reaction time at 35 degrees Celsius and give your answer correct to the nearest second. So in this case you would go along to 35, draw a straight line up with your ruler, hit the graph, draw a straight line across, and then you would write, well, there's 0.01, so that would be 0.011, 0.012, 3, 4, 5, so 0.0, in or around 0.015 there. Use your what would the give your answer to the nearest second. So use the graph to find the reaction time at 35 degrees Celsius, or actually I've done that the other way around, so let's go back to that graph again. What we should have done there is gone to the 35, I was taking it as time. Oh no, that should be sufficient, so that was the time there. And then just to convert that, we're talking about the rate of reaction is about 0.015, and remember that the time is equal to 1 over that 0.015, and if you do that in your calculator, you're coming in there at about 69 seconds, roughly speaking. So that's how you would do that. So we just need to convert that back into time again, as opposed to 1 over time, which was given in. What would be the effect of the reaction times if the experiment were repeated using 0 points? You need to think about this. It was what was the thiosulfate here? It was 0.05, so this is a 0.025, so it is a weaker solution, so the reaction times would most likely double. The reaction is twice as slow, so the reaction would be twice as slow, because remember the reaction time here is the time for the X to obscure, so it will slow down because it is a lower concentration. This is a lower concentration than the 0.5 or 0.05. Justify your answer. The rate is directly proportional to the concentration of one of the reactants, in this case the thiosulfate. I'll breeze through this one relatively quickly. Define the rate of a chemical reaction. So we've done that already. Explain clearly why there is almost an instantaneous reaction between aqueous solution of sodium chloride and silver nitrate, and you talk about there the fact that they are ionic compounds. Again, you see there's a bit of repetition there. Just remember the ionic compounds are free in solution. The bonds are already broken. All they need is the ions to collide. So it's a relatively straightforward idea. And then the next one, when hydrogen gas and nitrogen gas are mixed, 3 is to 1 volume in a room temperature, a sealed container, the formation of ammonia NH3 is very slow. Suggest 2 ways to increase the rate of the reaction. Well, you can increase the rate of the reaction by increasing the temperature of the reaction, is probably the easiest one. And you could also increase the pressure, and this in turn would increase the concentration, or you could add a catalyst. Increasing the temperature will mean more collisions, and those collisions have sufficient energy. The catalyst will lower the activation energy, the more effective collisions. And increasing the concentration, more molecules will be closer together, and this will mean then more collisions per unit time. So any one of the 3 of those. Describe how you would measure the reaction time of 10 cm cubed of 1.0 molar hydrochloric acid solution, 50 cm cubed of So this is essentially to measure the rate the balanced equation. If you're given the additional solutions along 0.1, that will give different concentration. How would you measure the rate? So you place the thiosulfate solution effectively over a page, and on that page you have an X marked, and your conical flask, we've looked at this back. In any case, you look up that experiment, and then you use your eye, you look down, and as you add in the HCl, this X will become obscure over time due to the production of sulfur. And then you would do that for each of those different concentrations, and you repeat the procedure effectively, and then you find the reciprocals 1 over time for each one of them. So that's just taking the time and dividing it into 1 for each of the times it takes, and dividing the rates by the corresponding thiosulfate concentrations will give a constant as you see along the time. Rate divided by concentration will equal some constant. And then, so the draw reaction profile diagram for an exothermic, again, that's the one we showed earlier. Exothermic reaction indicate clearly on diagram activation energy and the heat of the reaction. So there you have it again. We marked that in earlier. That's exothermic. Just because we have it here, maybe what we should do is show what it would look like for an endothermic reaction. What you would have is your normal axis again, but in this case you would have the reactants, and then you would have an activation energy, and then the products would actually have more energy than the reactants, and that would be endothermic. Now it wasn't asked here, but just so you know, and that would be delta H there, and then this would be the activation energy EA, and that is for an endothermic. I see it has not been asked in these questions.